So I think it's just about time to get started. Welcome. Thank you for coming to this talk on Lambda calculus. From the slides, I think maybe you get the impression that this is about object orientation, but we're in the sort of functional track room, so this is going to be about functional programming. And there will be some real-world functional F# and Elixir talks later on today that you should totally go and see. This is less of a real-world thing. It will be practical in that we will do a lot of live coding, but the subject matter is sort of less so. Yeah, so what is this? Is this a talk? This is a talk, just to clarify. This is the talk. It's going to be me, Einar, working at NRK, the public broadcaster in Norway, and Jonas.
Yeah, I'm Jonas from completeness.
And we will be talking. We will be having sort of a dialogue. It's not going to be the usual monologue that you get from a conference talk usually. And yeah, is that enough for a disclaimer?
I think so.
Yeah, so I tried to warn people on Twitter that this is going to be sort of an unusual talk about an unusual topic. But seeing as you're here, you must be the kind of people who like unusual talks about unusual topics, so that's good. We will be talking about the Lambda calculus, and the Lambda calculus is a theoretical model for computation that was, I think you can say, discovered by Alonzo Church in the 30s.
Yeah.
So it's quite old.
Yeah.
And it is, what is it? It is a Turing complete formal system.
Yeah, and it has function abstraction and function application.
Right.
And it kind of executes by having variables and substituting things.
So this is at this point quite abstract. But we will...
I think the main thing to take away is that we have functions.
Yeah, we have functions and not so much else.
Yeah.
It's sort of, so I think the motto of this talk is everything is a function. I mean it really, everything is a function. All you have is function, it's all functions.
Yeah.
Yeah.
So in some of the kind of batteries included languages, you have things like numbers.
Yeah. Yeah, and this is kind of a thing that you hear all the time about functional programming, that there's so much math in functional programming. We don't even have numbers, okay? So if you don't like math, you don't make math in Lambda calculus, and there is no math.
Yeah, so if you're afraid it's going to be math heavy, it's a good idea to not implement numbers, then you can't do that much math.
Yeah. So we sort of, if we want to, if we were sort of math geeks and wanted to invent numbers, we would sort of have to use conventions for that, right?
Yeah, so if you were at Andreas' talk yesterday, she mentioned the Why Functional Programming Matters paper. There's a talk that John Hughes and Mary Sheeran gives that has the same name based on the paper.
Yeah.
We stole one slide from that talk. And this is kind of how you do numbers in Lambda calculus.
Yeah, so
this is like Haskell code, I guess.
Yeah.
Because they're Haskell people.
Right.
So the idea is that a number is sort of, in programming, you use a number to do something several times.
Yeah, so
if you have a number in Java, what you want to use it for is for I equals 0
until x.
And do the I plus plus less than x.
Right, so there is really no distinction between, say, like the number 5 and the concept of doing something 5 times.
Yeah, they're mostly for looping.
Yeah, exactly, yes.
So the way, and we're going to get back to this when we have some Lambda calculus to work with, but the way we're going to do numbers later is the number 1 is a function that does something 1 time. The number 2 is a function that does something 2 times.
And it's very convenient because if you wonder how large a number is, you can just count the f's, and then you know which number it is, right?
Yeah. So which number is larger is easy to tell because it's the largest.
Yeah. So the manyness of the number is built right in, so you can just by glancing at it, you could tell which number is bigger than the other, right?
Yeah.
It's very intuitive,
and
in some sets, it's an abstraction that is very concrete because it is what it is, nothing else really.
So introducing the language.
So this is now the language syntax, yes.
Yeah, it has 3 things. So not a bunch. We have variables, we have function abstraction, and we have function application. So variables are just things like foo and x and y and stuff like that.
But you use those to, you bind them to functions, right?
Yeah, so they're usually bound by some parameter.
Right, yes.
And we have function abstractions. This is like in F# you'd write fun x and then some expression.
Yeah, so you introduce a function.
We use a dot instead of an arrow and things like that. And application is like in F# or Haskell or whatever. You just put a white space between the function and the argument.
Right, and the with the function abstraction, so the x is sort of the one parameter for the function. So all functions have one parameter, and the u is the function body, right? Yeah,
so you typically get the same things with like curried functions in order to take several arguments.
Yeah. Mm-hmm.
Yeah. So I'm not going to spend a lot of time on the trees, but
yeah, we'll sort of to have a working evaluator for Lambda calculus, we will be using a tree representation.
Later, right? So every u in this syntax can be like an expression, so it's a recursive data structure, so we can draw it like a tree.
Yeah.
So this is a small tree, this is a somewhat larger tree. So this expression corresponds to this tree.
Yeah. And then you have a sort of big tree.
Yeah. So like this larger expression becomes this larger tree.
Yeah.
And then we have the same expression, but we write. So it's different notation. We write the full Lambda expression on each node.
Instead of those abstract things.
Which is mostly to get it large enough so that Totoro can live there.
Yeah. Okay, so now we've seen pretty much all the language because we've seen the syntax, but we have...
Yeah, so we have enough to like build an expression.
Yeah.
But I guess we're wondering like, how does it run?
Yeah, so this is sort of the semantics, I think.
Yeah, so this is like how a program executes.
Yeah.
If you have something like this, then this happens.
which is quite intuitive.
So here's a Lambda and some expression. So it's a function application where the function is a Lambda and the argument is whatever.
Yeah.
And what to do, this notation means that you substitute this other expression for x in U1.
Right, so if there are any x's in U1, you're going to replace those with U2, right?
Yeah.
Mm-hmm.
Yeah, so...
Yeah, you say that down there, I think.
Yeah, so we kind of remove this part, replace this x, and this is the argument, so this goes where the x was.
Yeah.
So we end up with this.
Okay.
So we're not... If you have implemented a toy language yourself, you might have used something like a scope or environment, and then you look up. So when you call a function, you kind of add the binding that says that x is 2 within this function, and then when you get an x, you look it up in an environment.
Yeah.
We're not doing this because we want to do it more like you would do it by hand for some reason.
Yeah.
So when you get the function application, you do the substitution then, and you get like a new expression back.
Yeah, so in the case, the x just disappears. It's not going, you're not going to use the x to
you don't keep track of an
code.
environment, so that's kind of different than how you probably would do it if you made your own Lisp or something like that.
Yeah.
And it's not completely unlike how you learned that functions work in like school. So if fx equals x plus x, then f of 2 equals 2 plus 2.
Yeah, because you just replace the x's with the number 2.
Yeah.
Right? Yeah. Mm-hmm.
So I think that's the essence of Lambda calculus.
So now you know you need all you need to know in some sense.
Yeah, and then you get then you do that over and over again until you don't find anything you can reduce further.
Right, so this is sort of simulating doing it by hand in some sense.
Yeah.
Which is all we're going to automate anyway. But
so you look for Lambda here with an argument, and then you do the substitution, and you look for Lambda with an argument in the result, and then you do the substitution and so on. If we just print the results, like every intermediate result, we get something like this.
Right.
And we're going to...
Yeah, so if you live coded a Lambda calculus evaluator and had it running, it might do something like this.
Yeah, right. So we want to get something like this back from a running program.
Yeah.
So we're about ready to build the program.
So we've done program design, which is kind of rare in the industry.
So we want to start with a string, parse it into something like this, and then reduce it, and reduce it again, and we want to print the output, right. Which we have to kind of unparse in order to get.
Yeah, which is
back.
Going from the tree back to a string representation. Right?
Yep.
And we're going to do this, I think, using two teams of developers. The one team is going to be me. I'm going to do parsing, and Jonas will be doing the unparsing and the reduction.
Yeah. So, yeah, first thing to do is to make a type.
Yeah.
Should I do this? Or you?
Yeah, you can make a type.
I don't know how to use Max.
Can you see this? Is this large enough? Good.
It's Alt-Enter to do stuff.
Yeah.
Yeah. So we want to have a type for expressions. And like we said, it could be a variable. Variable is like a string. I still don't know how to do the bar thing on a Mac. Yeah. It can be an application, which has a function and an argument. Or it can be a Lambda, which has a parameter, a string, and some expression.
Right, that's going to be the body of the Lambda expression.
Yeah.
Right, so now we have this recursive data type.
Yep, and let's see, if you want to do the parsing bit.
Yeah, I can do the parsing bit. So we're going to have to do sort of a recursive parsing then of that correspond to each of these things, right?
Yeah.
And variables are going to be quite easy because it's going to be some sort of identifier. We can have some arbitrary rules for what a legal identifier is.
Yeah, we probably don't want white space in it since that means function application. Otherwise, we'll mostly.
So we'll work with that. And then we need some way of parsing the lambdas or the function abstractions. Those are going to look like lambda symbol and then some identifier, and then a dot, and then some arbitrary lambda expression. We're going to need to be able to put things in between parentheses, and this is because if you have sort of sequence of lambda expressions, you might want to control sort of the application order, right?
Yeah, so if you look at the tree at the bottom, if you don't use parentheses, then the first application will be like the two leftmost expression. The second will be the result of that application, and the
because it's going to be similar to sort of partial application of a curried function, right?
Yeah.
So it's going to apply this.
If you would like the second expression to be applied to the third expression, you would have to use parentheses around those.
You would include parentheses around here, right? And that's it.
Just scroll down.
I can scroll down.
There's a secret slide.
So to help us do this, we will be using a useful library called fparsec, which is a parser combinatory library. And it really does most of the work. So it's going to be mostly one-liners for us, which is good. Right, but I'm going to start by creating a small helper function. It's going to call it a parse, and it's going to take some fparsec parser and a string and apply the parser to the string. And the reason why I'm doing this is you have a built-in function that comes from fparsec called run. That's going to return either a success result or for a failure result.
So that's a good thing, but you want a bad thing instead, right?
Yeah, I want, because we're doing live coding, I want a bad thing instead.
Yeah, so you want some exception instead of...
I'm just going, if I have a failure, I'm just going to throw an exception.
Yeah.
Also, I don't care about how far I got in parsing the string and stuff like that, so I'm just going to throw those things away. I just want the successful or the failure things blowing up. So did you, yeah, I think now we have this helper function, which means we can actually start doing things using fparsec. So I can do things like, fparsec comes with a bunch of built-in things, built-in sort of primitive parsers that you can combine to create more powerful parsers, and that's what we're going to do in this talk. So one of those is called lower, and what lower does is it parses exactly one lowercase character. So if I give it a string like, I don't know, NDC, it's going to successfully parse the character n out of that string. Now, of course, if I give it an uppercase n, it's going to complain because it wasn't a lowercase thing, right?
Yeah.
I can easily combine or compose parsers in fparsec. So this is an fparsec operator that lets me try either a lowercase thing or an uppercase thing. So now hopefully this is going to be successful. And I can sort of iteratively create more powerful parsers.
We want like a bunch of those letters.
Yeah, so now I want at least one of those. And now I get a list of characters back. Of course, if I do something like this, it's not going to parse the exclamation marks, right?
Yeah.
And now I'm practically done with my variable parser, but let's see. Yeah, I'm going to need a recursive parser for expressions. And this is sort of a little bit of mechanics. The thing is, I'm going to need to refer to a parser before it's completely built. So I'm going to use something called create parser forwarded to ref.
Yeah, so this is kind of machinery we need because we're dealing with a recursive language.
Yeah.
And we also want to kind of build up the parser as we go. So the exp parser will be kind of more feature complete the further along we get.
Yeah, so we will be continuously sort of overwriting what's in the ref cell for expression parser ref, and that's going to sort of let us expand.
So to begin with, it will like parse variables, and then later on we will parse an expression.
Right. Now, so now I have sort of, here's my unit test. What I want to accomplish is I want to be able to apply the expression parser to the string foo and get, well, this must be a variable foo. So I'm going to first, I'm going to create a little helper function, which is really parsing just the string itself, and then I'm going to wrap it in this var thing afterwards. Let's see. I almost had it, actually. I think I can just...
Yeah. You have a list of characters. So
I have a list of characters.
Turn that into a string, it's good.
Yeah. So I need to apply some function to transform it from a list of characters into a string. So I'm going to use another fparsec operator that allows me to sort of transform one kind of parser into another kind of parser.
Yeah, so this doesn't consume any more input. It just does something with the result, right?
Yeah. So actually I think what I'm going to need to do is I'm going to create an array. It's a little bit cumbersome, actually, to create a string from a list of characters. So I'm going to create an array, and then I'm going to pass that to the string constructor, and then I'm sort of done.
Do you need the program?
Sorry?
Oh, right. No,
I had one too many here, I think. So, well, something like this. And now I'm sort of ready to create my var parser.
So now you just need to turn a string into like a var of a string.
And basically I'm just going to do the same thing once more, which is this, right? I'm just going to pass it into the var. And now I can, I think, do xparser ref. But it's going to be this one, right? Okay, so now I have my first iteration of the expression parser, which just handles these var things. And as you can see, the expected output is this. And I'm just sending it to be evaluated, and I get bool back true. So this must have worked, right?
Cool.
Right, so a little bit more complicated, but not much, is parsing Lambda expressions, the function abstractions.
Okay, so with this part, the parser begins to get like recursive, because the Lambda expression holds an expression as its body.
Yeah, so the body could be an arbitrary expression again. So now it's getting more interesting.
Okay, so this is when it start to need kind of the X-parser machinery and those things.
Yeah, exactly. So I'm going to actually split it in two parts because I'm going to parse. I'm going to parse this thing first, the lambda and the identifier, and then I'm going to parse the dot and the expression body. So I'm going to create a helper parser, if you will, using another one of fparsec's built-in parsers. It takes the character that you want to parse, and then it creates a parser that parses, looks for that character, right? So this parser is going to accept exactly the lambda character and nothing else.
Yeah, because in this expression we need like the lambda and the dot.
Yeah.
Then it's nice to have.
And I'm going to use another one of parsec's means of combination, which in this case, well, now this var name parser is useful again because I want to parse another string, right? And what this thing does, this strange thing with the dot, is it combines the two parsers, but you only keep the result from applying the latter one, right? The one to the right.
Yeah, so because the dot is on the right side, you keep the right.
Yes. So if I put it over here, I would have kept the lambda, right? But I want to keep the variable name instead. And similarly, I want to parse the dot. And now it gets more interesting because here's the sort of the recursive thing, right? I want to parse an arbitrary expression. And now I want to combine these in a way that gives me both the results, not just the one to the right or the one to the left. And I can use a function called pipe2. It takes two parsers, applies them, and then gives me...
Yes, I know you're doing a function that takes two arguments.
Yeah, a function that takes two arguments, one from the sort of the output of applying this parser and the output of applying that parser.
So both of those succeed.
Yeah, so if both of those succeed, I'm going to get a name and a body, and I can create a lambda,
Nice.
right? And that's pretty much it. Now I can update my expression parser and says, okay, it's going to be now either a lambda expression or a variable expression, right?
Yeah.
So if I do something like this, I have a more powerful parser that is capable of parsing this also, and this one, hopefully.
All the tests are green. Good.
Yes, so we have two green tests. Yeah, so a little bit. This with the parentheses is really preparation for the application, but well, I'm going to do it sort of bottom up with the parentheses first.
Yeah, sure.
So I'm going to need a parenthesis parser. And again, if Parsec helps me, I think I can just write the code and you'll understand what it does. So I'm going to try that. So let's see. And what does this do? So between is another fparsec function, and it says I'm going to apply this parser in between these two other parsers, and I'm going to keep the result from the thing that's in between. So I don't care about sort of the output of parsing the open parentheses.
Yeah, you only need the parsing to succeed and
yeah.
Carry on. Yeah.
Right. And this is now parenthesis parser. Getting a little bit cumbersome to write this. Let's see. I think I'm sort of done with everything except the application. So I'm going to combine those. Let's see. Into a single parser, which is everything but the application. And I can update my expression parser to be this new parser. And, well, now I can parse things that has parentheses around them. And I can have a lot of parentheses, and it's still going to sort of work nicely. So it doesn't care about the parentheses.
Nice.
Right. Now sort of the tricky part, which it turns out not to be so tricky if we have...
if you have like fparsec arrow?
Yeah, exactly. And if we realize that, well, we sort of need to think about...
If you like command tab back to the slides.
Yeah.
We have like a plan for this.
Yeah, we have a cunning plan for this, for doing this correctly. So we're going to need to do it sort of left associatively, and well, you know, Parsec knows that sometimes you need to do things left associatively. So let's see, there is
parse like the entire thing so that we end up with a list of expressions, and then we want to combine them into
a tree of applications.
Yeah.
So we have a sequence of expressions, 1 to n expressions, and if it is more than 1, then you're sort of going to need to combine them. And if it's just 1, well, it's just going to be the result of doing exactly
so
that.
if there's a function that just does that for us, that would be nice.
Yeah, so we have this something that's not an application, and I'm going to combine that. This is going to be the sort of the most opaque, I think, code in the presentation. So don't worry if it's a little bit what's really going on here. But what this is going to do, if it sees and successfully parses 2 not applications separated by white space, then it's going to combine it, right?
Yeah, so this parser here with the pcar, you're going to transform the result into the function that is going to combine 2 applications.
Yes.
2 expressions into an application.
Yeah. So I'm going to skip. I think this is the white space thing. I don't care about the...
Yeah, so I parse the white space and get like a white space as...
Yeah, so that's not terribly useful. We're not going to use the white space for anything. But we will use the not application that is meant to be applied.
Yeah, so there's an expression to the left and an expression to the right of the white space, and those are passed in as FNA, and you can make an application of them.
Yes, and I need another parenthesis. And now I have my finished app parser. And
you have your finished parser pretty much, I guess.
I think pretty much, because I can just, well, if the sequence just has 1 element, it's just going to be, then it's not going to be an application, obviously. So it's just going to be the same as applying the not application parser. So I can just say that my whole expression parser is going to be this application parser. Yeah, because
the app parser includes the not app parser in a way.
Yeah.
Yeah.
Okay, so this, I think, sort of completes. Oh, let's see if I can actually just for fun, well, you know, if I can do something like this also. Yeah, and now you can obviously see that this now applies. Well, this is the application of.
Yeah, so it's obvious to see that the tree is tilting the other way from that string.
Yeah, this is obvious. And for a more complicated example, we're going to see if this also evaluates true.
Yeah, so
now it must be correct.
This was like the large tree expression we showed in the slides.
And this is the Totoro.
Yeah, this is the tree where Totoro lives.
Yes.
And you can see that it's like several lines, so even in this notation it's possibly large enough.
Okay, so this completes the parser. So now we have some other things to do.
So we have like another slide. So we do parsing. We want to turn it back to a string, which I think is called parsing. And we have like a plan for doing that. It's like doing parse, but the opposite.
So it's undoing all the hard work that we just did?
Yeah.
Or the hard work that fparsec just did, I think.
Yeah, pretty much. So, oh, we've cheated apparently.
Oh, we have the...
Yeah, so this here wasn't supposed to be in there. I was supposed to write it now. So we have a parenthesis function that adds parentheses around something.
Yes.
And we can test it, and we should get like 2 smileys back, which is nice. We're going to need that in order to unparse.
And so basically we have all the cheats.
Yeah. Someone hasn't like cleaned up all the...
This could be me, you know.
It's probably you, since you did all this. So we're going to make recursive functions that work on this.
Yeah, because we have a
on this
recursive
expression type. Yeah. So unparse, and I don't actually write F# marks, so I don't know the same part of the language as Einar. So I like to do things like this. So unparse is a function, and we will do like pattern matching on the expression we get in. So if it is a variable, we will return the name of the variable. So this should be like an expression to a string.
And you can see by the magic of Einar that it actually does that.
Oh, yes.
Which is nice.
And there's the lambdas, which has a parameter and some expression.
Right.
And then we just
need to
turn it back into, let's see, it's like this to get the lambda.
Yes.
And the parameter is already a string. We want a dot.
Yeah, and then you need, well, some arbitrary thing.
Yeah, so the x is like an expression, so we call unparse recursively on that.
So it's going to unparse all the rest of it.
And then we have applications.
No,
so
it says unparse XML, which is strange.
I like autocomplete. It helps me out. And when we come to application, we have to like do some stuff in order to get the parentheses right.
Right.
We want parentheses around the lambda if there's a lambda as the function argument. So we have one match.
Yeah, so it's going to be 2 cases for application now?
Yeah, so we have one that matches if the function bit is a lambda.
Right.
And it has an
the
argument.
rest is whatever.
And we have to use our parent function and unparse the lambda stuff. Lambda px. Like this.
You really write F# kind of differently from me.
Yeah. And
this is very realistic with respect to working in the industry, right? So already we have the tension in the code base. I'm going to change his code. He's going to change my code.
Yeah. And we need to like consider whether or not to add parentheses on the argument as well. So we'll
Did you say what argstring is?
No.
Okay.
It will show up later.
Right.
But we just want to add parentheses around it unless it's just a single variable.
Right. So argstring is George's problem, and you're George?
I'm George in like 2 minutes. For everything else, we just unparse the function. And
I don't think you mean that.
I don't know.
Yes.
At all. And that's the reason why we have like an argstring function.
Because you're going to do it twice.
Yeah.
Right.
And argstring is also a function.
And that's also a recursive function.
Yeah, I didn't think you had to do that. You have to write the rec when it's like an and?
No, you don't have to write the rec. I'm sorry.
Yeah.
I'm just wondering why you didn't put the argstring in front of the... Well, never mind.
Yeah, argstring is going to call unparse.
Right, yes.
Yeah.
So it's going to be mutually recursive, right?
So variables are still easy to deal with. For anything else, we want to do x instead. And we want to put parentheses around the unparsed x. I don't know if any of this works, though.
Right. It could be that.
See what happens.
I think it's probably. I think it's it's indentation.
Do I have to do like this?
I think
I don't have to
probably.
do like this. I thought I had to do like this, and then I tried the other way, and it seemed to work.
Yeah, it could be that you have a sort of.
It could be that I wrote everything wrong.
No, I don't think so. Let's see. No. Not quite sure why it's.
I'm going to blame Einar's computer for everything that goes wrong. By the way.
Yeah. Oh, is it here? Yeah.
Oh, yeah.
Yeah.
So it shouldn't be necessary with the tabs, but they can stay. Yeah, so we can unparse one of those expressions from earlier, and we can do one of the unit tests. And I guess we're not going to spend a lot more time on unparsing.
Right.
We hope this works.
Yeah.
And I guess there are like a bunch of sheets down here as well.
Yeah.
I'll just let them stay and write here instead.
Yeah.
So
this completes the unparsing, right?
yeah.
So now all we have left is the evaluation.
Yes, so we want to do like the reduction evaluation thing,
Mm-hmm.
and then kind of glue the things together so we get like a running program.
Yes.
So reduction kind of consists of looking for something like this, which is an application where the function bit is a lambda, and then do substitution on it. So we kind of remove this and this and keep this body, but every a in the body is
going to be
replaced
foo.
with foo.
Right.
So we want a substitution function and a reduce function. So we're going to call it subst.
I'm going to guess that does substitution.
Yeah, and it's a function. And I'm pretty sure I'm allowed to do this without the tabs.
Yeah. Maybe just keep, if we have the right amount of parentheses,
Yeah.
it should be good.
So subst is going to take some argument, like foo, the
Mm-hmm.
thing we are substituting in, and some string we're looking for, the parameter name.
Mm-hmm.
And then there's the expression we're looking at. So if it's a variable v, then if v is the string, we return the argument. We substitute it for the argument.
Are you sure you want the commas?
Yeah.
Okay, good.
Yeah, we're going to pass in a tuple over those
Oh,
two
okay,
things.
right, yes.
And then arg, else we return the expression unchanged.
Mm-hmm.
And if it is, well, if it's application, should be simple, has a function bit and an argument bit, we just want to call subst recursively on each bit.
Mm-hmm.
So we do subst arg as f and subst.
Yeah, so you're sort of calling recursively down the tree.
Yeah.
Yeah.
And rebuilding an application.
Yes.
Should I be worried about the lines? The red line? Not yet.
Probably not.
Uh,
We'll worry later.
And the last case is if it's a lambda, then if the parameter that is bound by this lambda, the p, is equal to the thing we're looking for,
Yeah.
then if that variable occurs within the lambda expression, it's bound by that p instead of referring to the thing we're replacing.
Mm-hmm.
So we can leave it as is.
Yeah, because you're sort of shadowing what you're looking for. Is that it?
Yeah.
Yeah.
Oh, right. I need to have like all the arguments on each line.
Yeah. You should have worried.
Then we don't do anything with it. We just return the same lambda. And I'm writing random symbols here. And otherwise, we need to do like the same thing as we did in app. We just recurse down and look for variables.
Right.
So we make a new lambda in the same parameter. And we do subst arg as x. And I think that's it.
Yeah, so the only place where you're really doing any substitution is in the first line, right?
Yeah, so the whole thing is we're looking for a variable that has the same name.
Yeah, exactly.
And the rest is machinery in order to get to the variables.
Yeah, right.
So we have a substitution function. We're going to use it in our reduce function. And we want like a result type for reduction. So we're going to call reduce and look for something to do like the substitution on.
Right.
If you don't find anything, the expression is on normal form.
Right, because then you can't really reduce it any further.
There's nothing more to be done with it, so we have kind of finished evaluation. If we do find something, we will return sort of the next expression that we can do more work on.
So
do the substitution and return the result.
Right, yes. So hopefully you'll reach normal form, but we'll see.
Yeah, if you never reach normal form, we don't terminate.
Yes.
And if we don't terminate, we're like probably Turing complete. So that's like
that's a big win.
So yeah, reduce as a function. It takes an expression. The thing we're looking for is an application where there's a lambda with a parameter and a body, and there's some argument. Don't need this. And then we return a next thing.
Right.
And we substitute the body of the lambda with the argument. And I might be regretting that I did. Let's see. We substitute a for p in x. So we substitute a for the parameter of the lambda in the body of the lambda.
Yeah, exactly. So you want, inside the x, you want all the p's to turn into a's. Is that right?
Yeah. The others, well, easy case at least, is variable v. It is necessarily on normal form.
You can't really do much with that.
No, and it doesn't like contain a new expression that we can look into.
Right.
The rest of this is just going to be like going down the tree and look for stuff. So if it's a lambda, we have to
we're going to call
look for something reducible in the x. And then we have to rebuild the lambda if we get
so reconstruct it, yes.
Yeah. So we're going to do like match, reduce x with, and if it's a normal form, the whole thing is a normal form.
Yep.
If it is not a normal form, then we have some
you have some
reduced expression, some next step of computation.
Yeah, and that's going to replace the body of the lambda expression, is that right?
Yeah. So we do lambda p and the next expression.
Yeah, right. But it's going to be next of, right? So it's not just the...
So we want to carry on this next as well.
Yes.
And the kind of most cumbersome bit.
Yeah, because we're going to have to do it
because
twice,
we need to look in the function part.
Yes.
And then in the argument part.
Right.
So we look at the function, try to reduce that.
And if you cannot...
We'll do the other part first, I guess. So if we get a next function.
Because then you're sort of done.
Yeah.
Right.
We stop looking for more stuff to reduce. We only do like one bit of reduction each step.
Mm-hmm.
Then we have an application with the next function and the
Yeah,
old
you
argument.
didn't touch the argument.
And again, I need to do like next.
Right.
If it is on normal form,
And
then we have to look at the argument bit.
right, yes.
So we do match reduce A with,
And then it's going to be kind of similar.
yeah, so next, the next argument, and we get the next back. The function and the new argument. And if that is a normal form as well, then we know that everything's a normal form.
Right, because you have nowhere.
Yeah, that means we just
to look. Right.
looked all the way down to the variables, which are kind of the leaf nodes.
Yep.
And we didn't find anything to reduce.
Okay, good. So now we have the reduce function.
Yeah, so...
It means we're almost done, I think.
Yeah, so hopefully this works.
Yeah.
We're going to test it after we do like a tiny bit of assembly.
Yeah, so we're going to put everything together in one
We're
thing.
going to put most of it together so we can
Try
do like a test run and then do the REPL bit, I guess.
Yes.
So what we're going to do is we want to read some stuff, parse the stuff, and then evaluate the parsed stuff and write all the unparsed results.
Yes.
So on every step of having done
for each next, right? So
yeah.
You're going to do an unparse, so you can see what's going on.
Yep. So we'll start with, this is a function that might run forever.
Yay.
So just we call it run eval with some expression x. So this is an already parsed expression.
Yeah, so this is the tree representation, right?
Yeah.
Mm-hmm.
And we're going to like reduce the x. And if it is on normal form,
Then we're done.
we're done. We return like a unit value.
Yes.
And if it has some next expression,
And then you're going to have to write whatever that is.
so we do like, is it system?
I think you can do print.
That's probably easy.
Well, yeah. This is very enterprise.
Yeah, we're doing like the...
This is .NET interop.
Yeah, and we're doing like the side effect, the ugly bits anyway, so we can use right line. So we want to unparse the result we got.
Yep.
And write that. And then call the run eval recursively.
Yeah.
So what was the test expression called? Is it like appx?
Yeah, that's the expression, yes.
Yeah, so we can do like a test run on appx.
Yeah.
Yeah, so we get...
Yeah, so you can see down there, this is hopefully the same thing that was on the slide, right?
It's possible.
Yeah.
We can like go back.
So if you can just memorize what's...
Lambda, lambda, b, lambda, a, b, a, and so. It looks kind of similar.
Yeah, it has more or less the same shape, so it must be correct.
Yeah. Okay, so we want to make like a REPL.
Yeah.
I think that takes input from like standard in and then parses it.
Mm-hmm.
Which is also going to be recursive because it might run forever.
Yeah.
And we'll call it the REPL, I guess.
Yeah.
And now we do like parse, and then it's exp parser.
Yeah.
System console read line.
Yeah.
Is it like this?
I think so.
Yeah. And well, we can just do run eval on the result.
Yeah.
Since we did the kind of throw exceptions instead of doing result types, it's just going to blow up if we do something wrong.
Yeah, so that's good.
Yeah. And then we call I guess we can do like this returns a unit thing.
Yep.
Yeah. So if everything works now, we can start the REPL. And I don't know, the Lambda thing doesn't work here. No,
Yeah.
the index there.
It works there, so you can sort of...
Yeah, so there's an awkward bit where we type expressions in this window still and then copy-paste them into there.
Yeah.
The REPL. But we should be able to do things like lambda x, lambda y, y. Stuff like this.
So what would be the expected output from that?
Bar, I guess.
Yeah, because the foo is bound to x, but there is no x, so
yeah,
it's going to get lost.
So
yeah.
Clearly we have a working lambda calculus evaluator.
Yes.
Yeah. So it's a very useful language.
Yeah.
It's not clear what it does other than like, doing reductions.
Right. So and we were thinking a little bit about this, about Turing completeness. And in some sense, I think we arrived that Turing completeness is about giving you a bunch of rope and the ability to form a loop.
And hang yourself in it.
And then suddenly your program can hang.
Yeah.
Which is nice. This is as much power as you can hope for in any
so
programming language.
Kinda,
really,
it implies that things might run forever and never stop.
Yeah.
And other than that, it is like a definition of what is effectively computable.
Right.
So every algorithm should be possible to implement any algorithm in a Turing complete language.
Right.
So the kind of formal definition is that if you can do useful things like addition, and also you can screw things up and run forever, then it's probably Turing complete.
Yeah. I think maybe to illustrate that, sometimes you hear people talk about, well, it's Turing complete, and things like, well, what can F# do that C# cannot do, and stuff like that. And to sort of illustrate that this is sort of a stupid question to ask, we're going to try to make a little bit of math to show the distinction between what we call the Turing completeness and the Turing convenience, because some languages are more practical for doing some things than other languages, even though they're all sort of like Turing complete or church complete or whatever you want to call it.
And just while you're talking and creating some numbers we might need. Those are amongst the more useful ones, I think.
Yeah.
So, like I mentioned earlier, we're going to pretend that the number is a function that does something as many times as the number.
You don't think 1 is a useful number? Not for our purposes. So you just create as much math as you need.
Yeah, you don't need like... We could try to create all the numbers, but there's a lot of them.
Yeah.
So we're skipping some.
Yes. This is a very pragmatic approach.
So I've decided that having only 2 is like bad because it's hard to tell if you're doing addition or multiplication.
Yeah.
So it's nice to have like 2 and 3.
Right. So just to be clear, what we're trying to accomplish here is...
So in order to prove that it's a useful language, we're going to decide that these things are numbers and see if we can do addition on them. So we want some function that can take this as an argument and this as the other argument and return something that we're like able to pretend is the number 5.
Yeah,
so it should be lambda f, lambda x, then 5 f's and an x.
Yeah, so it should produce the same result as if we just wrote 5 using this convention.
Yeah,
right.
So it should take like 2 arguments.
Right. Already we have quite a few lambdas. So the A and the B, those are going to be the numbers, is that correct?
Yeah.
And then we're going to need to create a new number sort of on the
so
fly.
we do the lambda f, lambda x thing.
Yeah, because all numbers start with lambda f, lambda x, right?
And now we have an f that we want to apply the right amount of times.
Yeah, but that's all numbers do, right? It does something
so if we
a number
do
of
like
times.
AF, then the number A will apply f a number of times to something.
Right, so you sort of have the looping built into the number.
And if you do like... So what we're trying to do is apply the f b times to x and then apply the f a times to the result.
Yep. That's perfectly clear. So this is, we claim, the function that does addition on these numbers, right?
Yeah. So
if you can now copy all of these things together.
So we want like the 2 number, and we need to add some extra parentheses.
Right.
And the 3 number.
And now there's going to be a bit of calculation down there. The sort of the proof will be the final line, right? If you can count the f's, and we have 5 f's, then we have indication that this is a sound approach.
It doesn't work like great at the moment.
Oh.
Did I mess up with some?
So do you have like unmatched parentheses, or?
Do I have something that is not? Oh no. Let's see. We need to start the REPL again because everything blew up. It kind of runs forever, at least.
Yeah.
Is that like close enough?
Oh, this is awkward.
Yeah, so this is kind of the great payoff at the end, where everything just runs smoothly and everyone understands that.
Right.
Lambda calculus is a useful language.
Yeah.
Should
we try to get sort of...
can I do like...
Should we cheat?
We should probably cheat.
Let's see if we can cheat.
Are you better than me at cheating?
I'm not sure. Let's see. Should we take one of these other things and just sort of apply all of it?
Yeah, remove that one.
Well, remove what?
Do the garbage can thing and run everything in this file.
Right. So we're going to try again now, or?
Yeah, we'll see if we have time to do another try. We can see if the... Oh no, it's this slide.
Do you have your...
Where did all my numbers go?
I think it's probably... It's either higher up or further down.
I guess. All right, we're at the end of the file, and we're
so here are
sort
all
of
the
beyond
other
all
things.
my sheets.
Yes.
So where there's comments, we're still in
So
the
here
sheet
we
a
are.
bit. So let's see if each number works. So nothing works.
Oh, great.
I think that kind of sums up the talk then.
Yeah.
I'm not sure. And do we have like a plan C?
I'm not sure if we have a plan C.
So now we have a REPL. We can start it. REPL. Don't need those there.
I think we're pretty much out of time, but perhaps we can get it running.
The good thing is that you can do lambda calculus by hand, so you can kind of tell that this prints the right result.
Right, and one thing you could do, if you're all writing this down, you could go to well, maybe I can actually show it if I'm online. You probably shouldn't go online, but let's see. That's probably sleeping as well. Well, this is a hypermedia-driven lambda calculus evaluator running in Azure. It's written in Suave. You can put things in there.
Oh, right. So we have a plan C.
So if you can just copy everything in there, we should be able to see it running.
That's incredibly useful to have like running in the cloud.
Yeah. So now you can sort of, it gives you next links whenever it can sort of continue working. And now we have, I think, 5 Fs.
Yeah, and we already have like the name 5 for it. So everything works.
Perfect.
Yeah, we are out of time. This thing runs forever.
Yeah. So this is
clearly Turing complete.
Yes.
Thanks.